All right, folks. Well, I want to get into some of the interesting, gory details for Lisp this time around. So I want to take a look at some of the efficiency issues with Lisp, and I want to take a look at the underlying C implementation of Lisp. So taking a look at how our Lisp code is actually getting represented as C code. So behind the scenes, it all gets turned into structs and unions and pointers and whatever else is going on. So we're going to take some time and just see what that actually looks like. Yep. Let me get the right beast here. So again, we want to see how the different data types are implemented and what kind of an impact that might have on speed and storage. What kind of things happen with recursion and iteration? Can we come up with any ideas on how that knowledge lets us write more effective Lisp? So the code that we're going to be looking at is in this address, so you can go off and grab the header file. It's got a whole bunch of the definitions for different chunks of Lisp in it, and that's what we'll take a look at in just a second. So what we're going to see is that Lisp creates this union of all the possible data types it creates, and essentially says, a Lisp union can be any one of these things. So it can be, the data for an integer or a real or a character or a string or a whatever. And so there's going to be this Lisp union type that's defined. And then each of the data types that it's a union of will have their own collection of different properties in a struct with different fields for all of the different pieces of information that are relevant to that specific data type. And then objects, which are going to be kind of our generic Lisp item, our generic Lisp data type, right? Since we've got these dynamically typed items that could refer to an anything, is going to be a pointer to a Lisp union. So you've got all of the individual specific data types implemented as structs with a variety of different fields for each. A union is just a union of all of these different types, so it's saying it could be any one of these different things. And then an object is actually just a pointer to one of these Lisp unions. So it's a pointer to something that could be any one of these different data types. So that's how we get this kind of abstract, top-level, untyped thing that we can associate different types of values with over the course of time. So let's just take a quick look at that. So this is, apologies for the difficulty viewing here. Oops, let me get how we try the right one. So you can find a list of all of the different data types, an enumerated type, just specifying all names for all of the different types that are out there. You can find structs for each of the different data types. So a struct to represent a cons, or to represent a symbol, or to represent a character, or a short float, or long float, or a ratio, or a rational number, a big num, a type, anything that you can specify, a structure, a stream, right? All of these things have their own data type and their own struct with a bunch of different fields for that specific data type. And then our Lisp union is just saying, okay, anything that's of type Lisp union can be any one of these things. And if it's a ratio, I'll refer to it by the .rat. If it's an array, I'll refer to it by the .a, etc., etc., etc. And then our objects are just pointers, right? Object is just type def to be a pointer to a Lisp union. So an object can essentially be a pointer to any one of these things. And whichever one it's a pointer to has got a whole bunch of different fields specific to that data type. All right, and then you can go through and have a look at the collections of fields that are associated with a long float, or with a complex number, or with a character. Right? So all of the different relevant data is stored in there someplace. All right. And then if we find a cons, a cons is basically created as just a struct that's got something for the car and something for the cutter. So those are both just pretty much pointers to objects, right? So again, we've got, if we're thinking about a cons, we're creating a new element that's got a pointer to the head thing and a pointer to the rest. And let me organize my windows here. When we get into the implementation of functions, there are a huge chunk of sort of built-in functions in Lisp that are actually provided directly as C macros that generate C code. So if we take a look at some of these, if I can find the right ones, you'll be able to see different mappings for car to this, right? So we've got a C macro that's saying if we're accessing a car, we're going to do it by going through the pointer and getting the, so going through our object pointer and grabbing the car field from the struct for that cons, or if we're accessing a cutter, or if we're accessing, you know, the car of the car of the car of the car of the car, right? We just say, okay, from our object, go through that stream of pointers to get to the right one. And since this is all hash defined, right, this is a text substitution before compilation. And this is one of the reasons why if you take, you know, the car of the car of the car of the car and there's a null pointer in there somewhere, the list ends in there somewhere, you get a runtime crash because it's trying to do these pointer accesses. And it's just doing these text substitutions at compile time so that during execution, this is actually a pretty efficient operation, right? It's just going straight through, blat, you know, follow pointer, follow pointer, follow pointer, follow pointer, return, you know, and give the result. All right. So we can go through and see a whole slew of different macro-based implementations, and we can also see that most of the functions that are prototyped in this, and we'll take a look at some of those in just a second as well, go through and expect to be given a type, parameters of type object, and, you know, return values of type object, right? We're returning pointers to a Lisp union that could be any one of these data types. So you can take anything as a parameter, you can return anything as a return value, and what's really being passed around is always just, in fact, a pointer. Right, so if we, again, bounce through and take a look at some of the various functions that are provided, you know, things like a GCD function. Some of these are hardwired to take specific data types. Right, you can see definitions for a huge sum of the so-called built-in functions for Lisp in terms of, you know, less than or equals and testing what the data types are, returning appropriate values, things like doing left shifts or right shifts. All of this stuff is pretty much built in. You can see operations for counts, right, for absolute values, for lengths, right, where again we're taking an object and just returning whatever it might be. So you can go through and see what a huge portion of the different Lisp built-in components are actually implemented as at the C level, and get some kind of an idea of the, you know, how the implementation of a language like this might actually work. All right. So again, when we're looking at things like car and cutter and catter, it's just a straight plow through, right? Straight text substitution for the actual C pointer chain that takes you to where you want to go. And again, with all of these different data types, they're simply structs that have got a bunch of different data fields for the portions that they need. If you've got things like rationals, then the fields of the structs might include the values for integer, the structs for integers that are appropriate. If we take a look at how strings and bit vectors are actually implemented, they're basically just character arrays, right? Since we're just talking about essentially a a sequence of characters or a sequence of bits that are actually just implemented as bytes. If you see things like vectors or arrays, they're actually stored as an array of objects, or an array of objects, since the objects themselves are pointers to whatever could be in there. If you look at the various fixed types of arrays, those will actually get stored more effectively as, an array of integers, an array of longs, or whatever it might actually be. So when you go through and create arrays of fixed types, it can get a more efficient implementation at the C level. All right, and things like you'll see functions in there to create a list that go through and take the size of the list as a parameter, and it's essentially saying, okay, well, let's go off and create a list of this size where all of the elements are just these objects, right, which are just pointers to whatever they might possibly be. So you start getting a feel for what the underlying implementation looks like, and therefore you get an idea for where the efficiencies and inefficiencies come in. So if we look at our data types, right, strings, when we go through and access them, we're actually accessing a character array someplace. And so we can get fairly efficient access to strings. If we can't use something as a string, then if we can use it as a vector, that's kind of our next best access time in terms of efficiency. Or arrays are better than lists or sequences, but they're not as good as vectors. And you get this kind of chain of efficiency. So obviously, if we've got iteration, that's going to be more effective than general recursion. Tail recursion is going to be more effective than general recursion. You can get the iteration constructs to compile more efficiently, reliably than tail recursion, just because not all compilers are going to do good optimization for tail recursion. If you know that your compiler does good optimization, then it's not as big a deal. But if you just don't know, then you're better off taking one of the kind of iterative constructs. Do times and do list are better at that than some of the others. A couple of things to watch out for just in terms of general efficiency notes. If you are using tail recursive functions, then try and avoid the dynamically scoped stuff, because that will definitely mess up the effectiveness of your tail recursion. All right, just in terms of other considerations when we're playing with our Lisp code, obviously we're trying to be efficient, but efficiency is both the runtime and development time. So how much work is it going to be to maintain your code? How often is your code going to have to change, and how difficult is it going to be? And what's the trade-off between the right level of intricacy to get ideal efficiency versus maintainability? Right. So the usual kind of common sense programming tips. Avoid side effects where you can. Avoid things like eval when you're using this. Some of the other higher order functions aren't too bad, but eval in particular creates an environment to go through and evaluate what it's doing, and that can put a pretty substantial drag on your runtime behavior. Don't use dynamic scope unnecessarily. Again, that can put a drag on the runtime behavior. There are a few things that you can do in terms of just readability and maintainability, actually using the names for things, but I think most of this is fairly common sense. All right, I will leave it there now. Again, I just wanted to introduce some of the ideas, some of the thoughts about how this stuff might get implemented behind the scenes, right? At some point, Lisp has got to be turned into something that runs efficiently on the machines that we're working on. And that's an important consideration whenever you're looking at a language. How does this actually work under the hood? Okay, I will leave that there for now.